So, here's what we got today. It's okay. You were very animated. I hate to interrupt a good story. It's not a good story.
No, it's what I got on my AP test, so.
Oh, okay.
Well, it was average.
Sometimes that happens.
Yeah.
Yeah, I can
Anyway,
relate.
so yesterday
I'm
or
below
on,
average.
way back last week, it seems like an eternity ago, we talked about the four fundamental forces, and the first one we figured out is gravity. Now, this is somewhat relative to today. So today, if you get a chance, or you see me, go out and look at the night sky. So this is looking down from on top of our solar system. This is not to scale. But there's the sun, here's the earth, and here is Jupiter. Okay? So Jupiter is as close to the earth as it's going to be between now and like the next 170 years. Okay? So the cool thing about this is that it's known as what we're calling opposition. Okay? So there's a couple of things that are important in terms of how you're going to view it and the math. So if you look at the gravitational attraction between you and Jupiter, you are gravitationally attracted to Jupiter because you have mass and Jupiter has mass. Okay? Jupiter has a lot of mass. This wasn't quite big enough to turn into a sun. If its mass, they figure it was about 4 or 5 times bigger, it would actually have a strong enough gravitational field to start a fusion process, and we would have 2 suns, and that would have been really cool, but that didn't happen. So, you're standing here on Mother Earth. You are attracted to Jupiter because you have mass and Jupiter has mass. So, today, if you look at this equation, that would be like big G, mass of you, the mass of Jupiter, and the distance squared. So it's still a huge difference. But today is as close as you will ever be to Jupiter, okay? Between now and the next 107 years, all right? So realistically, y'all were 18, that puts you like at 125 when this happens again. Might be around there. Maybe not. So, what this means, and the reason that they say that it's in opposition, and this is how you can figure out when you can go look to find Jupiter. So this is looking up down on top of our solar system. So this is like the north pole of the Earth. So you're looking down on top of the Earth, okay? And we'll talk more about this later, but the Earth spins counterclockwise. So as you're going around, the Earth is spinning around like this. And so this is the dark side of the Earth. So, like if you're right there, that's like at midnight. So if you want to see Jupiter, so when you stand right here on this border between lightness and dark, that's sunset, as the Earth stands this way. So tonight, if you're outside, look to the west and you'll see the sun setting. If you look to the east, you'll see Jupiter rising. It will be the second brightest object in the star other than the moon. So it's the biggest planet. It's also as close. And so when you say that a planet is in opposition, that means the sun, the earth, and Jupiter are all in the same line. So tonight, and you can see it very clearly, especially if you have like any kind of pair of binoculars. You can go out there and just look at it with that. Especially if you can get outside away from the city lights. It's pretty easy to see Jupiter. So, especially if you go out maybe like 8 or 9 o'clock at night, it should be up about right there above the horizon, okay, which is, I know, not a very technical term, but if you go and look, it's going to be up about right there. So, if you want to go out, you won't see this again. It won't be this close again in your lifetime. So, just kind of a cool thing.
Wait, so what time should we go out then?
Anytime, like after 8 or 9 o'clock would certainly be good enough. That way it'll be above the horizon. You won't have to worry about the city lights interfering with it so much. But yeah, just literally go out, look to the east about 8 o'clock or 9 o'clock tonight, and you'll be able to see it. Because it's supposed to be clear tonight, so you don't have to worry about any cloud cover.
Okay, I'm trying to think what side my house is at.
Can't help you with that one.
Me neither.
Can't help you with that one. Okay.
I think it's
So-
west is my day.
So the second one we'll talk about is the electrostatic force. Sometimes you see this called the electromagnetic, okay? Same thing. So this one and we won't do any computations with this, but the equation is F equals some constant Q1, Q2 over D squared. So this is the most diverse of all of the forces. This is what allows us to be here having this conversation. It's what allows oxygen molecules to exist as diatomic. It's why we have water. It's why we have this earth. If we didn't have the electrostatic force, which, and in other words, if the universe was just made out of neutrally charged particles, okay, like the universe says, you know, I'm not feeling any charged particles. I don't feel like making charged particles. I'm going to make everything neutral, okay? Cool. We would not be here having this discussion. Because if everything was neutral, then you would never be able to form water. You would never be able to form DNA. You'd never be able to make anything like that. So electrostatic force just exists between charged particles. So electricity kind of does some cool things. So if I take this and like just touch the other side of this, okay, I complete a circuit. So what's happening is that electricity, there's a potential for the chihuahuas to flow from this end to this end, okay? Now, grab my hand, okay, there it is, okay, now,
Wow.
okay? Now, we're gonna have a kumbaya moment.
1 second.
So we're all gonna make one big circle around.
Wait, do it again.
And then we're gonna hold hands, and we're gonna make one big electric field, okay? So, come on, stand up. So this is one big kumbaya moment. Okay, all right, come on. Okay. All right, come on.
Go this way, guys. Come on. Go this way. Let's
We're
go.
all right. I don't like this.
Look, Marilla, I'm right here.
Spread out.
Go for it.
Okay. All right. Okay, grab. Okay, now, Meg, I want you to like let go of Riley's. Okay, touch again. So here's the cool thing. Itch, okay? So, touch again. So here's the cool thing. So look at how quickly that got transmitted. So we're all holding hands, right? Okay, so do that again. And as soon as you touch, okay, let go. Or hold on, somebody's up. Okay, now let go. So touch it again. So that's the cool thing about it. So that electric field is being transmitted all the way around us. So she touches it over there. That electric field is completed that entire circuit. So all this is because there's the potential for chihuahuas to move. So when we touch this, the chihuahuas are completing this big circuit, and we can make noise. Okay, we're good. That was enough of the kumbaya moment.
My real question is who does it?
No, but like I know. I think yours is like real.
So, today, we're going to be talking about friction, okay? So, friction is one of the great manifestations of the electromagnetic force. So, let's say it's getting kind of, now that the heat wave is kind of broken, it might be a little bit cold in the morning. You're outside, okay? You rub your hands together. You're generating basically photons. And those photons carry heat, and that's what you feel. So, what allows you to make toast, what allows us to make light, what allows us to have graphite, what allows us to have ink, what allows us to have clothes, what allows us to see. So, with the great manifestation, it is the most diverse. So, when I ask you, hey, this is an example of a particular kind of force, unless it's gravity, it's probably going to be the electromagnetic force, okay? So, up to the early 1920s, that was cool. They thought, oh, here are the two fundamental forces. Gravity, electromagnetic. Everybody's cool with this. But they observed some things that they couldn't really explain. Like, you know, when I did with the balloon and put my hand up there, they said, there's some things going on, but we'll just kind of thump it underneath the electromagnetic force. So then along came a gentleman by the name of J.J. Thomson. Anybody remember from your Chem 1 days the particle discovered by J.J. Thomson?
Electron.
Huh?
Was it an electron?
He discovered the electron. He used cathode ray tubes. So Thomson discovered the electron, which is the short version. He won a Nobel Prize for it, and so did his son. It's kind of a cool deal. It was only father and son team that won the Nobel Prize in physics. So he discovered the electron. Figured out it was negatively charged. So the short version of what he did is that he shot the particles through, and then it's just like a battery. Like a battery has a positive and negative terminal. And so he shot these particles, he didn't know what they were, and shot them through this field, and the particles were attracted to the positively charged plate, and they were repelled by the negatively charged plate. Didn't know what they were, but he knew that they had a negative charge. So then, okay, well, if there's negatively charged particles, guess what? There has to be positively charged. Because if the universe only made negatively charged particles, guess what? We wouldn't be here having this discussion because everything would just go flying apart from each other. So, okay, well, if there's negatively charged, there has to be positively charged. And so, if you remember back to your Chem 1 days, the first kind of working model was what's known as the plum pudding model. Okay? So this, you got to keep in mind, the research at this time was being done in England at Cambridge University. That's where all kind of the leading edge was. And the other thing that's going to be important is that this research was being done by the physics department. Okay? The chemistry department was trying to figure out how to purify cocaine. Okay? Now, true story. Physicists were like, hey, whatever. Okay? Work kind of, literally, because if you look at the readings at the time, during the 1920s, the scientific community was kind of bummed out because they had at the time they had thought they'd worked themselves out of a job because they figured we had gravity, we understood the motions of the planets, we understood the electromagnetic force, and the thinking at the time literally was the only thing that we have left to do is to like fine tune the constants, and that was it. They literally just at that time, science said we're done. We've kind of got everything figured out. But all of a sudden, Thomson comes along and says, oh, whoa, 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 boys and girls. There's electrons. And they're like, oh, game's on now. There's electrons. There's got to be protons. Oh. Then it's like, okay, what are atoms made of? Now, the word atom comes from the Greek word which means indivisible. Because this harkens back to Dalton's atomic theory. So Dalton's atomic theory said that all atoms are indivisible. And that held for a long time. So, again, if you look at a physics book from 100 years ago, there's no mention of electrons, protons, and neutrons. They didn't know they existed. So then it said, okay, there's electrons. Oh, God, protons. And said, okay, great. What are these indivisible particles made of? Now, you got to understand, the physics department was in charge of this research, okay? So the classic story about how physicists approach the problem is that you give a Volkswagen bug to a physicist, and you go, what's the Volkswagen bug made of? I don't know. Let's slam it into a wall. Cool. Okay? So you get the Volkswagen bug up to about 20 miles per hour, you slam it into a brick wall. Oh, look, a bumper came off. That's kind of cool. And then, being physicists, you go, well, the 20 miles per hour is good, 200 is going to be better. Okay. So let's get it up to 200 miles an hour. Slam it into the wall. Ooh, look, there's glass. That's cool. Okay? Well, 2,000's got to be even better. Okay? So then it's like, ooh, there's an engine inside. Oh, that's cool. What's the engine made of? I don't know. Let's take the engine and get up to like 4,000 miles an hour, and we'll slam that into it. It's like, oh, look, there's pistons inside the engine. How cool is that? What's the piston made of? I don't know. So then you get two pistons running into each other at near the speed of light, and you see what's the piston made of? Oh, I don't know. There's little parts that make up the piston. And so that's basically how physicists approach this. So there's a guy by the name of Ernest Rutherford, and Rutherford did what's known as the gold foil experiment. Okay, and so gold foil is extremely thin, and that's why we use it, because it has a very unique property. You can basically gold foil is basically one atom thick. And so, being a physicist, he goes, what's the gold foil made of? So he took a radioactive source, thorium-238 if I remember right, And it would go through radioactive decay, and it would kick out what was known as alpha particles. Okay, they didn't even know what they were at the time. He just called them alpha particles. What it turned out, it was a helium nucleus without the electrons. Okay, now everybody has this vision like you could actually see these particles flying through the air. Okay, no, these were like the nucleus of a helium atom. Okay, you can't see them, because if it did, it'd be really easy to do the experiment. Okay, you couldn't see them. But what happened is that they took this phosphorescent material and wrapped it around this gold foil, and the room had to be darkened. So imagine that we darken this room. I have a radioactive source here, a gold foil right there where Morello is sitting, and then we're going to put this phosphorescent material around it. And every time one of these particles would hit the phosphorescent material, you would see a flash of light. So the only way they would know where these particles were interacting is they would see the flash of light. Okay, it's a very crude detector, but that's how it worked. And so he figured out that these were positively charged because he did the same technique that J.J. Thomson did. He had a positively charged plate, negatively charged plate. The particles in this situation went away from the positive and towards the negatives. Like, oh, great. And it worked out well, because if these particles had been ejected and they were neutral, he couldn't have used them. But because they were positively charged, they did. So particles come out. So here's this sheet of gold foil, and most of the flashes of light were appearing directly behind the gold foil. Okay, even though the gold foil was there, almost every one of these particles went straight through. So that would be like me taking this golf ball, throwing it at the cabinet, and most of the time, the golf ball just goes straight through. So even though it appears solid to us, in reality, it's empty space. Now, every once in a while, literally like once in a million, one of the particles would hit, and it would come flying straight back. So Ernest Rutherford said that's like shooting a 6-inch mortar shell at a piece of tissue paper, and it bounces back. Okay, so that was kind of the analogy. Most of the time, these particles went straight through. But every once in a while, it would hit, and it would bounce back. So Rutherford at this point goes, we have a problem here, kiddos. All of that matter, which should have been like evenly distributed in the plum pudding model, oh, this is wrong, horribly wrong. So it said, okay, all of the positive charged particles are in one tiny, 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 tiny space. And that's also where all the mass is. So what happened is that here's the nucleus of the gold foil. Here's this helium, and most of the time, it's just going to go right past it. Sometimes it would hit and it would bounce off a little bit, but every once in a while, like literally every 1 in a million, it would hit and it would bounce straight back. But that was very, very difficult to do, because imagine that this on a relative scale, let's say this is a golf ball, and let's say this, and you're shooting like a marble at it. And then imagine the odds of that marble hitting just right and bouncing straight back. And it's 99% empty space. So the odds of you hitting that and bouncing back are pretty small. So this created a problem. We're kind of screwed. No, literally, the science department, physics, we're screwed. Because it didn't make any sense to have all of that positively charged particles in one small space. Because if you try and put all those positively charged particles in one small space, they repel each other, and they should go flying apart. So they said, wow, we have to come up with a new force. Now, they were brilliant in terms of doing the experiments. They weren't so brilliant in coming up with the names. They said, wow, this is a really, really strong force, and it exists in the nucleus. What can we call it? Oh, how about the strong nuclear force? Okay, so that was the marketing technique. Okay, strong nuclear force. So the strong nuclear force has to be stronger than the electromagnetic force, which makes these particles want to go flying apart. Okay, so that's why it's called the strong force. Now I'm going to tell you straight up. Listen to me. Listen to me. Listen to me. The test on forces. I'm going to ask you. It's a multiple choice question. I'm going to ask you which is the strongest force. and it's the strong nuclear force. Don't miss this question. I'm gonna tell you straight up, it's gonna be a multiple choice question. I'm gonna say A, gravity, B, electromagnetic, C, strong nuclear, D, weak nuclear. Now, let me give you a hint. It's never, I'm gonna ask you some questions. The answer is never the weak nuclear force, okay? It's not something we need to study. The weak nuclear force is important. Without it, the sun wouldn't be producing energy and we wouldn't be here having this discussion. So the weak nuclear force is important, but it only plays out in very specific ways with radioactive or nuclear fusion processes, okay? So don't ever pick the weak nuclear force. The weak nuclear force, I'm going to list it. It's never the answer, okay? Don't ever pick the weak nuclear force. So I say, hey, what allows the book to fall? Oh, gravity. But what keeps this ball from falling through the table? Oh, that's the electromagnetic force. Oh, what holds the nucleus together? What's the strongest force? Strong nuclear force, okay? That's how it's going to play out. So I'm going to ask you, what's the strongest force? Strong nuclear. Don't miss this question, but invariably, out of this, in every class, there's usually one or two people that miss this question. Even though I tell you this is what's going to happen, don't miss the question, okay? All right. Now, so the thing about the strong nuclear force is that it's the strongest force, and this is where they did get a little bit clever. So each of the forces has like a charge carrying entity. So gravity, they think, is carried by gravitons. The electromagnetic force is interacted by photons. So they made up for the kind of boring name by the particle they think carries it, and it's called a gluon, because it was like, oh, this is the force that is the glue that holds the nucleus together. So the strong nuclear force is carried by a particle called the gluon. So not really clever on the name of the force, but they were clever on the charged particle. So without the strong nuclear force, we would not be here having this discussion. Now, the strong nuclear force is the strongest, but it also acts over the shortest distance. So you're not going to take two protons, they're going to be walking down the street kind of casually like, hey, what's up? And they're all of a sudden, they're going to go, oh, that's the strong nuclear force, and they're going to begin to pull each other together. If that was the case, it would be very easy to create new elements, because when you look at the atomic number, anybody remember what the atomic number is of an element?
Number of protons.
Number of protons. And remember, it is the number of protons that determines the type of atom. It isn't the number of electrons, it isn't the number of neutrons, it's the number of protons. So if it was easy to change the number of protons, oh, you need some gold? Hey, we'll just stick some protons together. Boom, here we have gold. Okay, there'd be not a shortage of gold. Oh, you want some carbon to make diamonds? Oh, we'll just change the numbers. Okay, you want helium? You'd have a party, you want some helium? We'll stick a couple hydrogen atoms together. Here you go. Okay, so it's not the case. It's extremely difficult to change the number of protons. So here's the best analogy that I can give, because I can say this because I grew up with 3 older sisters. So let's say that you have 6 girls that don't like each other, hate each other. Okay, hate each other. Like somebody said something about Snapchat, Twitter, somebody posted something on social media. They hate each other, okay? Like if they see each other walking down the hall, they will walk down opposite halls just to avoid running into them, okay? They hate them that much, okay? Now, but imagine though, you take those same 6 girls and you put them all inside like a Volkswagen Bug, okay? Now, if you take those same 6 girls, which hate each other, but you put them in a very, very, very small confined space, oh, we're best of friends. They're taking selfies, posting on social media, like, okay? Okay? They're braiding each other's hair. It's amazing, okay? They love each other. It's like, oh, we're besties, right? Okay? But if you get them outside of that car, they hate each other again. So the same thing is true with protons. If you have protons within the nucleus, it's cool, tight, okay, tight, best. As you get them out of there, they're not going to like each other. So we exist because of the deaths of previous generations of stars, all the iron, carbon, nitrogen, all the complex atoms that make you up. In the death of a star, it took a whole bunch of protons, smashed them together, threw on some neutrons to balance things out. And voila, we have carbon, we have nitrogen, we have oxygen, we have iron for hemoglobin, okay? We have oxygen for our atmosphere, we have nitrogen for our atmosphere, we have all of these things. So everything that makes you up as a complex atom came from the death of a previous star. So it's an old science cliche, but it's absolute truth, that we are all made of stardust, okay? So those first generations of stars hadn't formed, collapsed, made this complex atoms, those got kicked out, reassembled, and here we are. Without that process, we would not be here having this discussion. Okay, so gravity, strong nuclear, electromagnetic. Those are your three potential answers. Don't pick the weak nuclear force. It's not going to be an answer. Okay, I'm going to tell you this right now. Don't pick the weak nuclear force. All right. So now we kind of need to tie all of this in together. So when you look at motion, okay, and this harkens back to Aristotle and this idea of preferred states. So I take this block, I give it a push. Every time I do that, what's the block going to do? It's going to slow down, it's going to come to a stop. Now imagine if this was the magic frictionless block, and I gave it a push, what would it do? It would just keep going. So the first thing you have to get out of your mind is that an object at rest is not the preferred state, okay? That is not the preferred state. If I got it moving, it would actually like to keep moving. But the only reason it comes to a stop is because there is friction. You alleviate friction, you alleviate the need to keep applying the force. Okay, so when you look at these forces on this block, so here's this block, okay, sitting right here. So at this point, there's two forces that are acting on this block. Now, because we're going to be dealing with a whole bunch of different forces, we need to differentiate what they are. So when you see F sub g, that stands for gravitational force. In this class, okay, in a physics setting, when I talk about the word weight, okay, weight means the same thing as gravitational force that will only be measured in newtons, okay? So when I say, what is the weight of a block? I'm asking for the gravitational attraction as a measure of force between a block and the earth or the moon or something like that. Weight is not pounds. Weight is not kilograms. Okay, if I want mass, and that's the equivalent of pounds and kilograms, okay? If I want mass, I will say mass, which is in kilograms. Most of the time we're going to talk about weight, okay? Now, there's two ways you can figure out the gravitational value of this. One option is that you use the equation mg. So if you look on your equation sheet, okay, this is on there, Fg equals mg. So that's the mass of the object in kilograms multiplied by the gravitational acceleration of whatever planet that you're on, okay? Ours has a very specific acceleration, which you all know to be 9.80 meters per second squared. So here I have a 1 kilogram mass. So if I want to know what a 1 kilogram mass weighs, or what is gravitational force, I'm going to take 1 kilogram, I want to multiply that by 9.80 meters per second squared, and I'm going to get 9.80 newtons. So I would say a 1 kilogram mass weighs 9.80 newtons. If this was a half a kilogram mass, I'd multiply 0.5 by 9.8 meters per second squared. So if you know the mass, multiply it by g, there's your weight. So one of the big debates always is like, ooh, do I make it negative? Okay, it's always a debate. It's like, ooh, what's negative, what's positive? When you're calculating weight, just get the number. Okay, literally, just get the number. Then decide in the context of the problem, do I need to make it positive or negative? So in the course of this lab, because we're going to be dealing with vectors pointing in opposite directions, we're going to make that weight be a negative value, okay? Because that force is acting downward. So I'm going to make that a negative value. So when this thing is sitting here, okay, on top of that block, there is a gravitational attraction between this and this strange rock that we're on, and the sum total of that attractive force is negative 9.8 newtons. Now, why doesn't, if there's that force acting down on it, why doesn't it accelerate?
Because of the electromagnetic force
Created by,
the electrons in the atoms of that table. Maybe.
it's okay.
And the
We're good.
protons,
Yes,
too.
and with mostly the electrons, okay? Because the electrons don't like each other. And actually, it's kind of weird on an atomic level, like you've never touched anything in your entire life, okay? If by touching you mean like your electrons actually come in contact with each other, it doesn't. Basically what happens is that what you feel is like something being pushed away is basically is an electric field, okay? You feel an interaction of the electric field. You never actually touch anything. You're going, oh, that's so weird. It is, but go with it. So what's happening is that it's exactly what Morel said. This is providing an upward force, because if I just drop this thing, what does it begin to do? It begins to accelerate. So this force acting upward is what we're going to call F sub n, which is our normal force. And no, there's not an abnormal force, there's not a paranormal force, okay? This isn't Halloween, we've had this discussion, okay? There's just the normal force. Now, this is also on your equation sheet. Technically, your normal force is Fg cosine theta. For now, okay, we're not going to worry about the angle part of this. We're going to assume that everything is flat. Eventually, we will deal with inclined planes, but for now, we're not going to. So, for those of you that are trig nerds, what's the cosine of 0 degrees? 1. Okay, let's hear it for the trig nerds. Okay, always 1 in every class at least. Okay, so the cosine of 0 is 1. So technically, every time you calculate normal force, you're technically multiplying by the cosine of 0, but the cosine of 0 is 1, and we really don't need to write that out every time. So for now, okay, your normal force and your gravitational force are the same numeric value, but they're just opposite signs. So right now, my normal force would be, if I could write, that would help, a positive 9.8 newtons. Now, here's the whole key to this. So I've got a positive 9.8 Newton force, okay? I got a negative 9.8 Newton force. Doing some advanced math, what do those forces add up to? 0. So here's the golden rule. If all your forces acting on a system add up equal to 0, you're at a constant velocity. That's it. That's it. Now, that constant velocity might be 0. It might be the speed of sound. It might be negative 10 meters per second. So the beauty of every force problem is that there's only 2 options. Speaking of lack of electromagnetic force. Every force problem plays out one of 2 ways. Either the sum of the forces adds up to equal to 0, and there's no acceleration, okay? Or the sum of the forces don't add up to equal to 0, and you accelerate. And then if it's accelerating, guess what? You can only do one of the only 2 things you can do is something's accelerating. Speed up or slow down. Okay? That's it. Every problem you're going to have between now and the test, which will be like that Wednesday probably of homecoming week, literally, it's only, I have a 3-trick pony. Either I make it move at a constant velocity, and all the forces add up equal to 0, or I make it accelerate, and the forces don't add up equal to 0, and then I decide, hey, do I want this thing to slow down or speed up? Okay, that's it. Those are the only three potential options you can have on every force problem. That's it. Constant velocity, make all the forces add up to equal to zero. It's accelerating. Oh, the forces don't add up to equal to zero, and then decide, oh, am I speeding up or am I slowing down? Literally, every problem, that's the only thing that I can do. That's it. So when I write every problem, that's the thought process that I have to go through. Do I want Michael to speed up, slow down, or move at a constant velocity? That's it. Okay? So when this block is sitting here, 1 kilogram mass, all the forces add up to zero. Now, when you draw it like this, and you got to get used to the terminology, okay? So, oh, I hate this thing. There we go. What's weird is that, like, if you tap it enough time, it starts to, right? There you go. You got to get that ink settling down to the bottom. Those electrons get hung up here. I got to get the electrons down. I like that. Okay. Now, when you draw forces like this, and you're going to draw a lot of forces like this, this is what's known as a free body diagram. Okay? So on a free body diagram, and it has nothing to do with cost, it's just what we call it. On a free body diagram, you're going to act like here's the center of the block, and you're going to draw all the forces acting out from the block. Now, some people like to draw the forces acting from the edges of the block, okay? Well, they'll start here and draw the vector and start here, or you can draw it from the center. Historically, you draw them from the center of the block, but if that kind of freaks you out and you go, I want to draw them from the edge, okay, fine, draw them from the edge, but historically you draw them from the center. So, when I say draw a free body diagram, imagine there's a dot, and you're going to draw all of the forces acting on that. Now, right now, this is all we got. We've got gravity, and we got the normal force. Free body diagram. The other way I'm going to expect you to draw this is tip to tail, and you all have done the tip to tail method. This is why we did vectors first, okay? So if we draw this tip to tail, oh, there's my negative 9.8 newtons, which is my gravitational force. From the end of that, I'm going to come back up here. I'm going to draw my normal force, 9.8 newtons. I end up back at the origin. So no matter how many forces there are, if you draw them tip to tail, 2 forces, 5 forces, 100 forces, it doesn't make any difference. If you draw those forces and you tip to tail and you end up back at the origin, you're moving at a constant velocity or you're at rest, but you're not accelerating, okay? So when you draw vectors, okay, listen to me, when you draw vectors, and there's only one of 2 options, if you end up back where you started, you're moving at a constant velocity or you're at rest. The main thing being is that you're not accelerating. You can be moving, okay, you're just moving at a constant velocity. The other option is that you draw the forces and you don't end up back at the origin, you begin to accelerate, okay? Those are the only 2 tricks you have in town. That's it, there's nothing else. Okay, now, we're going to make it a little bit more complicated. So, one of the things we use a lot is this scale, okay? And it's cool because it's a digital one. So, the on-off button, fairly simple, hold that, okay? And it's going to turn on, okay? And it's going to read 0. But the thing with these scales is that you have to read 0 them depending upon how you're going to use them. So the other way that y'all are going to have a block of wood that you're going to use in the lab, okay? So if I want to figure out what this block weighs, if I knew the mass, which I don't, okay, I could just take the mass and multiply that by 9.8 meters per second squared, boom, there's my number. But I don't know what the mass of this block is. But what I can do, so I'm going to take my Newton scale. Now in this situation, I'm going to be using it vertically. So for those of you in the back, you can't see this. But right now it's reading 0.09 newtons. So this thing is thinking there's a load on it. So what I'm going to do is, there's a 0 button, okay? You just hit that once in the orientation that you're going to use it, and the scale should flip out, and then go back to 0. So right now I'm reading at 0. So I've re-zeroed the scale. So I'm going to take this, I'm going to lift it up, and I've got 3.86 newtons. Okay? So since I don't know the mass, I'm just going to let the scale do this. So when this block is sitting here, I got a negative force of 3 point, and I'm going to make this negative. There we go. Newtons, 3.86, it's horrible, newtons, okay? And I want to make that negative because that's acting down. The table is providing an upward force of positive 3.86 newtons, okay? Everything adds up to equal to 0, we're cool, right? As soon as I drop it, what does it begin to do? Why? What did I lose? I lost the normal force. Guess what? There's still gravity. Oh, look, it begins to accelerate because now there's no normal force. I let go of it. Oh, the forces don't add up to equal to 0. The block begins to accelerate. Okay? But we're going to sit here like this. Now, what I'm going to do is I'm going to measure how much force it takes to pull this block, and listen to me very carefully, 2 words. I'm going to measure how much force it takes to pull it at a constant velocity. I don't want accelerated motion. I want constant velocity. So now in this situation, I'm going to be using the scale horizontally, okay, on this orientation. So I'm going to take it, I'm going to hit that 0 button again. The scale is going to be reading 0. So I'm going to hook it up, and I'm going to pull this thing at a constant velocity. I get about 0.90 newtons, okay? Now, so the force is, this force, which is making it move, we're going to call this force applied. 0.90 newtons, okay? Now, one of the things you'll hear me talk about in the stories of this is that you're going to deal with 2 different types of mafia. There's the frictional mafia, and there's the gravity mafia, okay? So in this case, the gravity mafia is going, you good boy, okay? You want to move the block, you got to pay us some money, okay? So the frictional mafia always has to be paid off, okay? Because they're always there. Unless I specifically tell you that it's a frictionless surface and there's no frictional mafia, you got to pay the. It's like doing business in Chicago. You got to deal with the mafia all the time, okay? So what's happening is that the only reason that I'm applying a force of 0.90 newtons, then I'm pulling it at a constant velocity. So let's take the stop process a little bit farther. So I got a negative 3.86 and a positive 3.86. So if my applied force is 0.90 newtons, what do you think I'm paying to the frictional mafia? Negative 0.90 newtons. Okay? So the force friction, what we're going to call
I have a question.
F sub F, in this case is going to be negative 0.90 newtons. Now, miracle of miracles. I take 3.86, I add negative 3.86, I add 0.9 and a negative 0.9. I add up to 0. What happens? It's going to move at a, rhymes with the constant velocity. Constant velocity, winner, winner, chicken dinner. So, this thing is moving along, life's good, okay? I'm applying a force of 0.90 newtons. Now, here's what's important. The only reason I have to apply a force to maintain motion is because of the frictional mafia. If the frictional mafia goes away, and this is the magic frictionless block, which would be really cool, I could just tap that, boom, it would move it across at constant velocity. I would not have to keep applying the force. So the only reason, listen to me, the only reason you ever have to continue to apply a force to keep an object moving is because the frictional mafia is there. Okay? Now, I'm pulling this thing along, okay, pushing it along, and all of a sudden I get tired. I'm old, okay? I'm tired of pushing the block. As soon as I stop pushing the block, what does it begin to do?
Accelerate.
It begins to slow down. It begins to accelerate.
Decreasing.
It accelerates.
Oh yeah.
Oh,
That means that
accelerates.
it's going to be different from the force of friction.
Okay, now hold that thought.
Okay.
Now, when I was moving it along at a constant velocity, all the forces added up to zero. And if you were to draw that tip to tail, which is what you're going to do on the lab today, I always draw my gravitational force first. Okay, hey, there's negative 3.86 newtons. And then I've got my force applied. I got my force normal. I've got my force friction. Where am I going to end up?
Back at the origin.
Back at the origin, no resultant, I have a constant velocity, okay? I might be in motion, I might just be chilling out, don't know. If if all you know is that all the forces add up equal to zero, you have one of two situations. Either you're at a constant velocity and you're moving, or you're at a constant velocity and you're at rest. All you know is that you're not accelerating, okay? Now, I'm pulling this thing along and it's like, I'm done. Can't do it anymore, okay? The block is gonna begin to do what? Slow down, speed up.
Slow down.
Slow down. At that point, we lost the applied force. Applied force is no longer there. What force is still there, though?
The friction.
Friction. Okay, friction is still there, gravity is still there, normal force is still there. So as soon as I lose the applied force, what do the forces not add up to?
Zero.
Zero. At that point, what's the object going to begin to do?
Slow down.
Or accelerate, right?
Or yeah.
Okay, accelerate. The acceleration might be speeding up, the acceleration might be slowing down. Okay? It's just going to begin to accelerate. Forces don't add up to equal to zero. So now, if I were to draw that tip to tail, I'd go gravity. Here's my force friction. There's my force normal. Where do my vectors not add up? Where do they not meet? At the origin. Guess what? Now you have a resultant, and you're going to begin to accelerate. Does anybody remember in which direction you draw the resultant? From the origin out or back to the origin?
Origin out.
Origin out. It's the roux thing, right? Oh, good on you, mate. So there's my resultant. So if you have a resultant, guess what? You begin to accelerate. If you remember this lecture, yeah, if you remember this lecture, you have 90% of forces beat, literally. Because everything is only one of two things. I write a problem, what decision do I make? No. Accelerate or
Constant velocity.
constant velocity. If I accelerate, then what are my two options?
Speed up or slow
Speed
down.
up or slow down.
Wait, so-
Literally, when you read through this lab, okay, you're gonna have like a car that's gonna slow down, okay? What do the forces not add up to?
Zero.
Zero. You're gonna pull a block at a constant velocity. What are the forces gonna add up to?
Zero.
Zero. Literally, that's it, okay? Everybody says, oh, physics is tough. It's like, no. Make the forces add up to equal to zero or make them not add up to equal to zero. I'm not asking you to make an add up to like the square root of 111.4. It's a zero, okay? Goose egg, freshman, zero, okay? That's all you have to worry about,
Zero.
goose egg.
I have a question.
Okay, now, on your equation sheet, if I may, I want to see this for a
Can I
second.
ask a question real quick?
Yes?
Is force of friction always negative?
No.
No? Okay.
The force of friction is always just in the opposite direction of motion.
Always in the opposite?
Direction of motion.
Okay.
But typically,
So you can't-
you define where you're going, the direction that you're going is a positive value. So typically friction then is a negative value. Not always. If you're defining a negative velocity, then friction would be a positive value. Okay, but if you have positive velocity, friction is going to be a negative value.
Can you ever have like your force applied to be greater than the force of friction?
Yes.
Yeah.
It has to, or it won't move.
Well, yeah.
So, like,
but,
if I take this block,
I mean, how does it speed up then? That's what I'm confused. If it's
we'll get into Newton's third law. Hold on to that thought.
okay.
Okay, because then that's a debate about how anything moves at all.
Yeah.
Okay, we'll hold that thought.
Okay.
But it's Newton's horse. Okay,
Newton's force.
Newton's horse.
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 Okay.
Horse. Okay. Now, on your equation sheet, this fifth equation down. Whoa!
Wow, that was really good reflexes by me.
That
though.
was impressive. Wow. Hammer it down. That was about bad.
One was a train wreck.
Yeah, we can go back and watch that one. Okay. So the sixth equation down is this. So this is an absolute value. Okay, so that's going to be important. So this F sub F, what do you think that is?
Friction.
There's your frictional force. Okay? Frictional force. And then F sub N is your normal force. Now, this is the Greek letter mu. Okay? It's the Greek letter mu. Basically, it's a letter U with like a one side, like both sides to it. Okay? Now, that mu stands for what's known as the coefficient of friction. Okay? So that's the Greek letter mu, coefficient of friction. Okay? Now, so let me explain how this works. We do not have a coefficient of friction measuring device. So if you go to like, y'all probably out of Chem 1, y'all work with like the vernier probes, measure temperature, pressure, okay, that type of pH. There is no coefficient of friction probe, okay? I can't plug something in and hook it up and go, shine it on the surface and go, oh, the coefficient of friction is this, okay? You can never directly measure the coefficient of friction. So what we do is we measure a couple of things. We measure macroscopic things. We measure the frictional force, like for example, if you look at this example with the block of wood that we just did, this is what y'all want to do in the lab. So when I was pulling that block, number one, I know there's a frictional force, and this goes back to this Jedi Stoffel thing. You stop the force and you watch. So if I'm pushing something and I stop applying the force to push it and it slows down, oh, that means there has to be a frictional force acting on it. Because if there was no friction, it would just keep moving in a straight line. Okay? Same thing is true if I drop something, it's like, whoa, whoa. And it was like, Mr. Brookham, is gravity still effective in this classroom? I don't know. How can I check? Oh, I'll drop something. Okay? As soon as I begin to see that thing accelerate, I know there's gravity. Because if there was no gravity, I let go of it, it would just stay there. Okay? So as soon as you stop applying the force and you see an accelerated motion, that means there has to be some external force acting on it. Got that idea? So if I want to calculate the coefficient of friction as I pull this block, I want to solve for mu. So I want to get mu by itself. There's a couple of things about this. Because it's an absolute value, quit throwing things. Because it's an absolute value, there's a couple of things about force friction. It's never a negative value because it doesn't make any sense, okay, to have a negative value in terms of the calculation. You can have a negative value in terms of the situation. You might define the frictional force as being a negative value, but within the confines of calculating mu itself, it's never a negative value. So if I want to get mu by itself, mu is going to be, I'm going to divide both sides by force normal. So mu is going to be force friction over force normal. This is typically how we do this, and this is still like an absolute value thing, okay? So in this situation, I can't measure my force friction directly, okay? I have no force friction probes. I have no mu probes. But what I can do is that I can measure how much force it takes to pull it at a constant velocity. Oh, that was, whatever that value was, 0.90 newtons. Now, that's going to be 0.90 newtons. Then I'm going to divide that by the normal force, which we said was 3.86. So somebody take a calculator and take 0.90 and divide that by 3.86. 0.23. I'm good with that. Now, there's a couple of things, there's three things to remember about the coefficient of friction. First off, what units is that going to end up being in? Why'd you shake your head?
It's just a number.
Yeah, okay. Coefficient of friction is one of the very few what we call dimensionless numbers because it's newtons divided by newtons. It has no units, okay? So mu has no units. It's just a number. The other thing, so one thing to remember, there's no units. It's one of the very few things I will ever tell you, oh, this has no units, okay? Mu is almost always, mu is less than or equal to 1, okay? If you ever get a mu of like 4, 5, 12, you have done something wrong, okay? Typically, 1 is kind of actually like a theoretical limit. Sometimes you might get a little bit above that, but even that is exceptionally rare. So if you ever calculate mu and you get a big number, it's a train wreck. Something's gone wrong, okay? The other thing is that it's always positive, okay? So it's always positive because it's an absolute value. That's why it's not a vector quantity, because it wouldn't make any sense to say, oh, the mu of the block is negative 0.3. Doesn't make any sense because it doesn't have any units. It doesn't have a direction. It's just a ratio, okay? So when you calculate mu, keep three things in mind. There's no units, it's always positive, and almost always it's going to be less than 1, okay? Never, certainly a big number like 2, 3, 4, never going to happen. If you ever get a big mu, something's gone wrong. Okay, stop that camera. So, kinetic. So static means from rest. Kinetic comes from the Greek word kinesis, which means in motion, okay? So what we just did is that we found the coefficient of static friction. We pulled it along at a constant velocity. We figured how much force it took. Boom, there you go. So when you're driving your car, you put it on cruise control, you're dealing with kinetic friction. Now, static friction measurements is a little bit more difficult in terms of your technique. So when you do static friction, so I'm going to take this block. Are we going again? Mm-hmm. Okay. And what you're going to do is you're going to slowly increase the amount of force that you apply until the block just begins to move, okay? Until the block just begins to blush. So, now, this is also a classic example of just because you apply a force doesn't mean that you get movement or you get an acceleration. So if I pull on this block, and I'm up to about 0.5 newtons, so I'm exerting a force of 0.5 newtons. But it's not accelerating. Why? What's holding it in place? Friction. So I'm applying a force of 0.5 newtons, but the frictional mafia is going, you're not paying enough, we're not going to let you go. Okay, you got to stay. Okay, you get some more money, I'll let you go. Okay, so just because I'm applying a force doesn't mean I get an acceleration. Okay, now, if I increase that force until that block just begins to move, okay? So I'm slowly increasing that force. At some point, it just began to move. which looking at it was about 1.20 newtons. So mathematically it's calculated the same way. So if I want the coefficient of static friction, I'm going to take force friction and divide it by force normal. So my force friction, in this case, was how much force it took to make it move. How much force did I have to pay off the gravity mafia to? So in that case, that took me 1.20 newtons, and I'm not even going to put the negative sign in there because it's not going to make any difference anyway. It still has the same force normal of 3.86 newtons. So somebody take 1.20 and divide that by 3.86. 0.something. 0.31. So what you'll see generally, okay, is that your static friction is bigger than your kinetic friction. And the reason being is like that the block is at rest, so not only do you have to overcome the friction, but you also have to overcome the inertia, which is keeping it at rest. So in theory, your static friction is always bigger than your kinetic friction. And most of the time it is, but sometimes you have some variance, but that's pretty rare, okay? Got the idea? Okay, so stop that for a second. Lab, I'm just going to get you introduced to the first part of the lab today. So what you're going to do is, up here, you're going to calculate the coefficient of static and kinetic friction between the block and different materials, okay? So the first one you're going to do is a block of wood on a wooden surface. So you need to figure out the weight of the block. So what are you going to do? How are you going to figure out the weight of the block? Yeah, take your scale, hold it up like this, re-zero it, hit that button. In this particular case, this block weighs 3.92 newtons. So what I would write here on that first column, Fg is going to equal my normal force. So I would write down whatever your block weighs. Every block is different, so it's just going to be whatever that is. Then I want to do the force that it takes to pull it from rest. So I'm going to take this scale, I'm going to re-zero it, because now I'm going to pull it horizontally. I'm going to hook that up, and I'm going to see how much force it takes to pull it from rest, which was like 1.20 newtons, whatever that is. So then I'd write down that number right there. Then I'm going to calculate the coefficient of static friction. So I'm going to take 1.20, whatever it took to pull it from rest. I'm going to divide that by the normal force. I'm going to get a number. Then I'm going to do kinetic. So then I'm going to pull it along at a constant velocity. And you'll see with these tabletops, there's some variance depending upon the surface. So just kind of get a section where you can get a pretty consistent pull. So in this case, that was like 0.85. So on that kinetic friction one, I would write down, oh, that took me 0.85 newtons. And then I'd calculate the coefficient of static friction. I don't want to see all the calculations, but I want to see like the first row of those calculations of mu. Then we're going to test this with different materials, okay? So you're going to do aluminum. So you're going to take a piece of aluminum foil like such, okay? Lay this out, and then you're going to do the same thing. You're going to hook this up. You're going to pull it along at a constant velocity like this. And you're going to, from rest, static. Then you're going to do cotton. You're going to have a sheet of paper towel like this, okay? Pull that along, see what it takes. And then finally, the last one you're going to do is sandpaper. Put that down, boom. Now, which one do you think is going to have the largest coefficient of friction? Sandpaper. That's the whole point of sandpaper. Low coefficient of sandpaper doesn't sell very well. It's like, what'd you do? No, not a lot. Just kind of went over it. Okay, well, that's exciting. So, so that's going to be the first part of that lab. Got it? Good. Stop that. Back we go.
Okay.
Or is it going?
No, oh, well, now it is.
Okay. So, we really don't have any homework tonight. So tomorrow, we'll start with those coefficients of frictions, and then we've got a second part to that, which we were talking about. So, there you go. So no homework tonight.
Let's go.